Hi, good morning, everyone. Good to see so many of you. Yesterday was a very long day. We crashed with the ARC crash course sort of nearly into midnight. So it was a hard crash. Today will be a somewhat lighter day. That's the good news. We have the closing session is until 5, and that everything looks like we should be able to make it. So that leaves some time for some of you to relax after that, and for some others of you to work very hard on the spatial prediction contest. This morning, the only program you have this morning is the four speakers who will do sessions. Today they're going to introduce their topic. There is 20 minutes in the program, but if you need more, it's okay. If you need less, that's also okay. Then we just have a somewhat longer coffee break, which,
sounds awesome.
Has also value in itself.
Yeah.
Our first speaker is Anita Graser. Could you introduce yourself?
Of course, yeah, I can introduce myself. Thanks again for inviting me over. It's my first time at this summer school, and I have to get a confession out of the way. I'm a Python person. So also this workshop, if you attend it, will be in Python, but I hope it's structured in a way that it's not a problem, even if you haven't done much with Python before. So my research focus at the AIT is in analyzing movement data, and that's also what the workshop is about. We are analyzing all kinds of movement data, from human movement to vehicle movement, movement of goods, in order to make suggestions to improve logistics flows. So that's the background of my research. And today I want to present you a bit of the background first of why I started developing the MOVINGPANDAS library. So MOVINGPANDAS unfortunately has nothing to do with these guys, even though that would be really cool. But we don't do much animal movement research, unfortunately. If you have data on them anyway, I would love to have a MOVINGPANDAS tutorial with panda data. That would be awesome. Instead, it's about this pandas. So it's about the data analysis library of Python that is called PANDAS. And the motivation, as I said already a bit, is that we get a lot of different movement data sets all the time for different projects. And getting a feel for the data, exploring it, doing those first steps that you have to do before you can decide in which direction you want to continue investigating, is always some degree of awful, because there are no standard tools that you can just plug your data in and have a look at it. So I have summarized a couple of the issues that I regularly encounter in the blog post that is linked here in the bottom. And I just keep on developing this whole series about movement data in GIS and beyond. But mainly, usually you want to extract some of the key features of the movement data. So from this hairball of trajectories that you get when you visualize the incoming points and you connect the consecutive points, you maybe want to extract the origins and the destinations from this data set and find out what are the most common origin-destination pairs. Or you might want to calculate the travel times between those. So tools that can help you get there faster are what's needed, I think. And one of the big challenges that I've faced is the conceptual one, like what is movement data and how should it be modeled? On the one hand side, it's geographic, of course, because the movement happens somewhere. And of course, it's also temporal, because there is a sequence of the locations, which is very important in the analysis. So you could either look at it as geographic features with timestamps, as we do so often in the GIS world, or you could look at it as a time series of locations. So on the right-hand side, you see one of the examples. I think I took that one from the OGC moving features standard, this short comma-separated value example, which can be interpreted either way. So it could be a time series, or it could just be points with timestamps. So before starting to develop MOVINGPANDAS, I looked into what's out there already, and one thing I spent quite a lot of time on was the GIS, the usual GIS approach, and the approach that is used in spatial databases such as PostGIS. Then I also looked into ETSER's R package for trajectories, what they have been doing there. And I also looked into what computer scientists do, because there's this whole field of moving object databases, which is also really interesting on one hand, and on the other side, a little frustrating, because there are no established tools. It's all research prototypes, which are fit for teaching, which I think means they are not fit for production. I don't know, but that's what they say on their website. So as a GIS person, the natural reaction to movement data is, yeah, let's make a map, and the GIS certainly can deal with some kinds of movement data analysis. And yes, you can write SQL statements that can create trajectories out of the points. You just have to take care of always grouping by the object IDs and sorting by the timestamps, and doing that every time that you want to create an analysis. So the SQL statements that you need to write to do anything in a spatial database, starting from the movement points, are rather annoying and long and get complicated. So there's different approaches that you can do in a GIS. If you have movement data, you can have points or segments between consecutive points, and they can be timestamped, they can have additional attributes. But the large issue is that there is no built-in logic that ensures that you always get the points in the right chronological order for your analysis, or really anything else. So you have to always have some additional application logic that knows these points with timestamps are actually part of a trajectory and should be treated like they belong together. And the GIS itself doesn't really help you much with that. The other approach is, you can of course connect all the points that belong to the same trajectory into a line. Then you have the correct order of points, because that's fixed. But then you run into the issue that you cannot save attributes to each individual location anymore, because you can only save attributes for the whole line string. The only exception here is you can save one attribute to each node using the line string m, or measure variable, which I have experimented with. Actually, PostGIS has this trajectory support, where the concept is that you put the timestamp as an integer into the m measure. So you can do some things with this approach, but there's only one m measure for whatever reason, and that's already used up by the timestamp, so you cannot store any other attributes anymore with the nodes. So you cannot store the recorded speed at the location, you cannot store any other context information. That all would have to go into a separate table maybe, or yeah, it gets complicated. It's not a good approach. In our trajectories, although ETSER would certainly be better qualified to tell you about how that works, but they also store spatial points. And if you need to visualize the trajectory, you can also access the connections between the points to get a better view of the data than if you just plot the individual points, of course. But basically, it's also more focused on the geographic, I think, than on the time. One interesting thing the computer scientists that do moving object databases do that they don't just have linear interpolation between points. So I think both trajectories and the PostGIS trajectories, they always assume that there is a linear connection between the one point and the other point. In contrast, in moving object databases, the researchers actually go the extra way and specify for each segment what kind of connection happens on this slice. as they call it. So you can have linear movement between consecutive points, or you can have arc movement or constant movement. And this allows you to reduce the data set size considerably if you perform the appropriate pre-processing steps first. So this is taken from the documentation of the HERMES database, which is developed by the University of Piraeus. And they have extensions for Oracle and for PostGIS if you're interested. They do share their work. But there's also a separate one here from Germany, which is also, they don't even use a standard database as a baseline for extension. They have built the whole thing from the ground up as a teaching database where you can have your students experiments with all kinds of things. So these have been the approaches that are out there and that I looked into of how to model the data. But of course, that's only half of the story, because the other part of the story is once you have the trajectories stored in some way or other, you also want to analyze them. So the question is, what kind of functions for analyzing this data should you include in a library like that? And there is, first of all, of course, functions that work on individual trajectories. And I think they are essential, and those are the ones that I have so far mostly implemented in MOVINGPANDAS. And then there's a whole range of functionality that you would apply to pairs of trajectories or groups of trajectories, which give you more advanced capabilities as well. And of course, there's a lot of data manipulation and housekeeping functionality that you will also need to work efficiently. So let's just have a quick look to give you an impression of what kind of functionality I'm talking about here. So there are spatial primitives. So the question here would be, I have a given time, and I want to know where the object was at that given time. And PostGIS and HERMES, they call it differently, but they both have these functions. Either locate along for one timestamp or locate between for two timestamps if you want to extract a segment between two timestamps. The other way around, you could also have the question, given a location, when was the object at this location? So that would be interpolate point or add point. You also have questions about the distances that have been traveled, the directions, of course, and the extent of the whole trajectory. One thing that's interesting maybe to note here is that particularly the HERMES database, they have often two functions that are called similarly. So there is F direction, and there is also just direction. And the direction function would just give you the overall movement direction from the starting point of the trajectory to the end point, so it's like a global perspective. And then there is this F direction, which you have to supply with a timestamp, which gives you the local movement direction at this one timestamp. So that's maybe something to keep in mind, that the same function can have two different meanings depending on the implementations. Of course, there's also overall duration, and then it's always convenient to have some utility functions that compute speed, velocity of the trajectory, which again can be local between 2 points, or a global, or something in between if you have moving averages, for example. On the other hand, if we move into groups of trajectories, there are really a lot of examples in the literature of what you might want to implement here. The most obvious is always to have distances or similarity measures between trajectories, so you can cluster them, find groups, maybe extract the central movement axis of the group so you can reduce the data set size. Then, of course, you want to have some descriptive statistics, like how many trajectories do you have, what area do they cover, what's the density, or things like formation, is there flocking behavior or dispersal behavior, mostly from the movement ecology sides. And also, you can even compare different groups of trajectories. They could be different groups of animals, flocks, Do they move together and separate in the same group again, or do they intermingle, for example? So, as I already said, these group or functions for multiple trajectories are currently not implemented in MOVINGPANDAS yet, but I wanted to include them anyway in this overview so that you get a bigger picture of the topic. The functions I want to end with are the data manipulation function, and they sound kind of basic, but you would be surprised how tricky something like even clip or intersect can be with a library that's not built for moving object data. For example, I had a master's student whom I asked to do intersection work with post-GIS trajectories and land use polygons. And the first thing she realized was, yeah, post-GIS can do an intersect of a line string M with a polygon, but the intersection has lost all its M values, because ST intersection drops the M values. So you lose all your timestamps from your movement data, yay. Why? I don't know. Anyway, it's really complicated to restore the time information afterwards. And yeah, it's something I did not expect. I hadn't tried it before. I was like, yeah, that sounds like a good idea for a master thesis, try that. And then we run into those problems. Also, of course, you need range queries to do a spatial filtering of the data. PostGIS has this, I don't know if you've ever seen that, but this triple ampersand filter that's n-dimensional index, and that can take time, can take account of the time and the space of your data set. So that's really quick if you want to filter in PostGIS on spatial temporal data. Any spatial temporal data, doesn't have to be movement data, could also be something else. Then some tools already implement things like nearest neighbor queries, which is of course also very nice. And downsampling and generalization is also something that I have already started implementing because I think that's really useful as well. And not to be underestimated, the challenges of coordinate systems, like we already discussed yesterday, which will only get worse in the future, and visualization. So unfortunately, particularly the computer science people are not so much into visualizations. They are happy to have their data in their database. They don't need to look at it. So if you want to look at it, you can always export it in some GeoJSON file and then do whatever you want, but it's not really their main objective. So that can get a bit tricky if you use something from that direction. So why did I end up with PANDAS as the base for my developments? PANDAS has been developed in the context of financial modeling. So they spent a lot of time on working with time series right. So since I wanted to try this approach of looking at the movement data as a time series of locations, this seemed like a natural fit, particularly since there is already an extension for PANDAS, which is called GeoPandas, and which allows you to store geometries in the data frame. These geometries can be points, lines, polygons. So theoretically, we could even try do some aerial moving object work with this. I haven't looked into that yet. Currently, I'm still looking at point objects that move in space, but theoretically, the combination with GeoPandas would enable us to have aerial objects that change shape over time and move over time. And we should be able to model that as well, which would be really exciting in the future to try. These are just some of the core functions that are included in the trajectory class so far. So you will see all of these and more in the workshop, and of course you can also look into the repo if you're interested. And for all those who just see the code right now and who will maybe not attend the workshop, I included a couple of lines of how it works. Here, the first and the last line, really you can ignore that. Those are just for taking the time. And then I have one line for reading the data from GeoPackage format. The read file function is already provided by GeoPandas, so nothing to implement there. Then I just need to take care of setting the index on the time column. And I can read the data like a normal geodata frame and plot it. Here they are plotted with different colors for the trajectory IDs, so you can see it goes from 1 to 5. I have 5 trajectories in this data set. And then if I want to construct my trajectories, I just do a group by the trajectory ID on the data frame, and then I construct my trajectory objects out of that. And the output you can see here is the basic summary output that you get if you print the trajectory object to string. So it has a WKT string, and it tells you when the trajectory started and how long it is, and how many points are in each trajectory. So here the first one has 466 nodes, and the longest one has over 1,800 nodes. And then you can use the same function that we had before, but before the points were just points with timestamp information. And now you actually have trajectory objects which have a linear representation and can be visualized with the speed along the trajectory with 3 lines of code, basically. And I just want to add one last example, which I thought was really showing how helpful this approach of looking at movement as a time series can be. And that was based on a discussion on Twitter where someone said, could this be used for precision agriculture? And then I asked, what exactly do you mean? And he brought this example of this potato harvester. So they are tracking the potato harvester, and they're also counting how many potatoes are extracted. But the counting happens a couple of seconds after the machine has passed the location from where it extracts the potatoes, because there's this conveyor belt, and somewhere at the end of the conveyor belt, the counting happens. So if you just match the timestamps of the countings and the timestamps of the location, you get it shifted. So there is in PANDAS already this shift function that you can apply with an offset in any kinds of units, 1 second, 50 seconds. And it's really just this one line of code which lets you rearrange the whole data so the counts align with the actual position of when the potatoes were extracted from the soil. Instead, if you think of how you would do that in a GIS, particularly if you don't have regularly sampled data where you have one position every second and one count every second, but where those can be differently spaced, I think you realize that can cause quite some headaches, and certainly not be solved as elegantly as just writing one line of code. So in the workshop, we will have 3 notebooks to work with. The first one will give you an introduction to the PANDAS trajectory MOVINGPANDAS trajectory class. And then I have 2 more applied notebooks. One will look into ship analysis data, ship data analysis. And the second example will be bird migration data, which we can look at together to explore how the library works. And if you have movement data yourself, we can also try to work with that. So I'm certainly looking forward to all your feedback there as well. Thank you very much.